In these problems, we're going to be finding the electric field due to a particle, and we're also going to be calculating the force on another particle in that field. So we have two equations we're going to be using. The first one here is the electric field strength equation. So that's going to tell us E, which is the electric field strength. And it's going to tell us the electric field strength for a specific charge. So here, particle 1, that's our main charge in the question. And we're going to find the electric field produced by that charge. So that's this capital or uppercase Q there. So that's the charge of the particle whose field we are finding. So be careful there, because we actually have two charges in this question. We have particle 1, which is making this electric field, and another particle mentioned in the question, which is a test particle with a different charge. So there are two particles in the question, but we're looking at particle 1. And since we want to find the electric field strength because of particle 1, we're using the charge of particle 1 in this equation. K is a constant of value 9 times 10 to the power of 9 Newton meter squared per coulomb. That's going to be the same every single time. And then lastly, R, which is the distance away from the particle that we want to know the field strength, because the electric field is going to be different strength at all different points based on how far away we are from the particle. The further away we get, the weaker our field. So R, that's going to be the distance from the particle whose field we are finding. So notice all these things are to do with the particle whose field we are finding. So you might have multiple particles in the question. This equation just looks at one particle at a time. It looks at the particle whose field we are finding. So that's our first equation. The second one is then for finding the force on another charged particle in that field. So in this question here, we're told that there's a test charge at location A. So I'm just going to draw that on. Here's our test charge here. We're told that it's positively charged. So that's our test charge. And the second equation is going to be finding the force on a particle in the field produced by particle 1. So we're going to be finding the force on test charge here in that electric field that we already found due to particle 1. And to do that, all we need to know is the electric field strength and the charge of the test particle. So F here is the force on the test particle. E is the electric field strength at that point. And Q is the charge on the test particle. So this equation is all about the particle that we're looking at. So it's no longer particle 1, it's now the test charge or the test particle that we're looking at. And it's the force on that particle and the charge of that particle. And then the electric field strength at that point, which is due to the particle 1. So the E is going to be the thing in these equations that is the same. So we're going to be able to find E from one equation and use it in the other equation. Okay, so let's give the question a go now that we have that information. So let's read the question. We have a charged particle which produces an electric field. That's particle 1, producing the electric field. We then have our test particle of charge positive 4.8 times 10 to the negative 19 coulombs placed at location A. So that's going to be the charge on the test particle. So we can fill that in down here. That was our lowercase q was positive 4.80 times 10 to the negative 19. Okay, it tells us that that particle experiences an electric force due to the electric field from particle 1. We also are given information in the question. Here we've got the charge on particle 1, which we can fill in. That's the uppercase Q. It's negative 2.08 times 10 to the negative 18 coulombs. And we've also been given the distance from the main particle and to the test charge. So we can fill that in as well. That's 3.33 times 10 to the negative 7 meters. Okay, so that's all the information we're provided within the question, and we need to find two things. We need to find the magnitude and direction of the electric field due to particle 1 at location A. So that's going to be the E in our equation. That's what we're looking to find there. And then we'll look at the positives and the negatives to figure out the direction. The second thing we're going to find is the magnitude and direction of the electric force on the test particle. So that's our F down here. Again, we'll find the direction by looking at the positives and negatives. So when we put our numbers into our equations, we're not going to include the negative sign or the positive sign on our charge. We will just put the numbers in as they are, and then later on, we'll look at the positives and negatives to figure out the direction. Okay, so looking at our equations, the first equation has 4 variables. We know 3 of them already. So we already know the charge, we know the constant K, and we know the distance. So this one is ready to go. We can calculate out our solution. The second equation, we only know Q so far. We still need to find out E. And that's what we're going to find in this first equation, and we can then use in the second one. So let's give that a go now. Our equation's already rearranged for the thing we want to find, which is E, the electric field. So we can just go ahead and put our numbers in. K is the constant 9 times 10 to the power of 9, multiplied by Q, the charge of our particle. Again, we're not putting in the positives and negatives here. We're going to look at the charges later on to figure out the directions. Divided by the distance, which was 3.33 times 10 to the negative 7. And now all we need to do is plug that into our calculator to find an electric field of 169,000 newtons per coulomb. And I rounded that to 3 significant figures there. So that can go in here, 169,000 coulombs. Oh, sorry, newtons per coulomb. For the direction, we know that our main particle is negatively charged. And we also know that field lines always point from positive to negative. So therefore, we know the field lines are going to be pointing in towards the particle. And so at location A, the field lines are going to be pointing to the left, in towards the particle. So the direction of the electric field is going to be left at location A. If we had looked at this location B up here instead, it would have been down. If we had looked over here, it would have been to the right. If we had looked down here, it would have been up. So just because they selected location A and A is over here, we know it's pointing in towards the particle, so it's to the left. Okay, awesome. So we found E now. We found the electric field strength at that point. We got 169,000 newtons per coulomb. And that value is the same in both of our equations. So the E we found here and the E here are the same. So we now have enough variables to be able to solve this one here. So I'm going to copy that number down here, 169,000 newtons per coulomb. And we can now put that into our equation. We're looking to find F, the force. Again, this is already arranged correctly, so we just need to put our numbers in. Force is going to be the electric field strength, 169,000, multiplied by Q, the charge, which is 4.8 times 10 to the negative 19. And that's going to get us a force of 8.09 times 10 to the negative 14 newtons. So that's the force acting on the test charge at location A. When we write that into the box, we can use scientific notation. Instead of writing times 10 to the power of, we can just write E. So that's 8.09 E negative 14. And our unit is newtons. Now, the direction of the force is going to depend on the type of charge we have. Here, our test charge is positive, and therefore the direction of the force is going to be the same as the direction of the field, left. Since our positively charged test charge is attracted to our negatively charged particle. If, on the other hand, it had been negative, they would repel and it would be to the right. So a couple of things to be really careful about in this type of question. Firstly, we have two different charges. We have uppercase Q, that's the charge of the particle whose field we are looking at. And then there's lowercase q, that's the charge on the test charge, the particle that we're seeing, what happens when it's in the field of the other charged particle. So just make sure you get those the correct way around. And then we can use the electric field strength from one of these equations in the other one. In this question, again, we have a charged particle producing an electric field. So that's particle 1 here. We don't actually know the charge of this particle yet, but we know it's producing an electric field that can be felt at location A. It then tells us there's a test particle of charge negative 9.6 times 10 to the 19 coulombs placed at location A. So that's placed here. So I'm just going to draw that on. Here we have this negatively charged test charge placed at location A. And it tells us that it experiences an electric force of 8.11 times 10 to the negative 14 newtons to the right. So I'm just going to draw that force on here. It's experiencing an electric force to the right. Okay. We're also given in the question the distance between our particles. So in this one, we're going to be working backwards because we know the charge on our test charge and we know the force. So we'll be able to use those to figure out our electric field strength at location A. Then we can work backwards from there to figure out the charge of our particle. So first, let's go through and add all of our variables from the question. Down here, I've written out all my symbols for each of the equations to make it really clear what's going on. I've already filled out the constant. It's always 9 times 10 to the 9 for K. Okay, let's fill out what else we have. So from the question, the test particle has a charge of negative 9.6 times 10 to the negative 19 coulombs. Test charge, remember, that is the lowercase q down here. So that's negative 9.6 times 10 to the negative 19 coulombs. Okay, and it tells us it experiences an electric force of 8.11 times 10 to the negative 14 newtons. Then over here, we're given the distance between particle 1 and location A. So that's our R, 7.15 times 10 to the negative 7 meters. Okay, I think that's all our information. So we can have a look at our equations now. We can see we have both F and Q in our equation on the bottom. So this one, we have just one unknown, so that's solvable. The first equation, we only have K and R, so we don't have enough information to solve this one yet. So let's solve the second one first, and we can use what we find to help us again with the first. So I'm going to write out my equation to solve it. It's not in the correct form yet because I need to find E electric field strength. So I'm just going to rearrange it first. The original equation is F equals E times lowercase q. I want to get E on its own, so I'm going to divide both sides by lowercase q. So that's going to give me F over lowercase q equals E. So to get electric field strength, I'm dividing the force by the charge. So we'll do that now. My force was 8.11 times 10 to the negative 14 divided by my charge, which is 9.6 times 10 to the negative 19. Again, I'm not putting any positive or negative signs from the charges into my equation. I'm just putting the numbers in, and then I'll figure out the direction of the force afterwards using the positives and negatives given in the question. So I'll put that all into my calculator. That's going to get me an electric field strength of 84,500 newtons per coulomb. So I can fill that out here. Okay, so that gives us our electric field strength, E. I can fill that in over here now. And then we need to remember that the electric field strength is the same in both equations. Both of these E's are the same thing. So we know one, so we can fill out the other now. It's going to be exactly the same, 84,500 newtons per coulomb. So going back to our first equation now, I have Q, sorry, I don't have Q. I have E as well. And I'm trying to find Q. I just have one unknown left. So I can solve this equation now. First, I need to rearrange it though. So let's rearrange our equation to get Q. So I'm just going to write my equation out again. E equals K times Q over R squared. I want to get Q on its own. Right now it's divided by R squared. So I'm going to multiply both sides by R squared to get rid of that. So that's going to get me E times R squared on the left, and then K times Q on the right. And lastly, to get Q on its own, right now it's multiplied by K. So I'm going to divide by K on both sides. So that's going to give me a final equation of E times R squared divided by K equals Q. So there's my rearranged equation. Now I just need to put my numbers in. So let's do that here. So we had E, that's what I just calculated below. It's 84,500 multiplied by R squared. R is 7.15 times 10 to the negative 7. So 7.15 times 10 to the negative 7. I'm making sure to put that in brackets to make it super clear that the whole thing is squared, including the 10 to the negative 7. And then I'm dividing all of that by k, which is 9 times 10 to the power of 9. So I'm going to put all of that in my calculator to get out an answer of 4.81 times 10 to the negative 18. And I can fill out that over here. Again, I can use scientific notation. Instead of writing times 10 to the power of, I can just write E. 4.81 E negative 18. And our unit for charge is coulombs. Awesome. So same as usual, we've written out all of our variables, figured out what we know already, and then which ones we can solve. And then we used what we found in one equation in the other one to solve it. The last thing we need to do is figure out our directions. So let's have a look at this now. We know we have a negatively charged test particle, and we know it experiences a force to the right. So based on that, we know the test particle and particle 1 are attracting one another. So they must be oppositely charged. Therefore, particle 1 must have a positive charge. So because particle 1 has a positive charge, that means the electric field is going to be pointing away from it. So electric field is going to be pointing away from the positively charged particle. Therefore, our A is going to be to the left. And lastly, we can fill in our sign on particle 1, which was positive.